Hello everyone, welcome to this session. In this session, I am going to derive the steady flow energy equation that is called as a steady s.f.e.e. Here, the steady flow energy means where the energy at one section is equal to the energy at other section also. It will be the flow does for energy flow does not changes with respect to time. The energy will be remains constant, and that for that the equation what we are going to derive, that is called as a steady flow energy equation. And this is a part of the basic thermodynamics module 2 lecture 3. Here we are going to consider the certain flow systems. For that we have to derive the steady flow energy equation. The flow system where the flow of the fluid will be taking place. The systems like steam turbine, gas turbine, water turbine, pumps, nozzles, diffuser, all these are the flow systems. We'll take the one of the example here and we'll derive the steady flow energy equation for that system. The same equation is applicable for the all other steady flow systems. Here, the one of the steady flow system we will consider that as a steam turbine. In the steam turbine, the steam is entered to the system where the energy is converted into a work. The heat energy contained in the steam will be converted into a work and remaining steam will be discharged at the outlet. So what the energy contained at the section 1 at the inlet we have to take, and that is to be equated with the energy at the section 2 at the outlet. And here the Q1 1 to 2 amount of heat is entering to the control volume and W amount of work is output is producing. And here the focus on the certain the volume of the fluid we are going to consider where the actual energy conversion is taking place. And here certain arbitrary datum line we have to take, and from that datum line the distance up to the at the inlet we are going to take as z1 and at the exit we are going to take it as a z2, and all the parameters at the section 11 and section 22 will take, then the total energy entering to the section 11 and section 22 those to be equated in order to have the steady flow energy equation. Here we'll take let P1 equal to pressure of the working substance entering the control volume in Newton per meter square. V1 specific volume of the substance in meter cube per kg. V1 velocity of the working substance entering the control volume in meter per second. U1 specific internal energy of the working substance entering the control volume in kilojoule per kg. Z1 height above the datum for an inlet in meter. P2, V2, V2, U2 and Z2 are the corresponding values for the working substance leaving the control volume at section 22, and these values are the corresponding values what we have defined here. Then Q1 to 2 is heat supplied to the control volume in kilojoule. W1 to 2 work done by the system in kilojoule. Now considering 1 kg of the working substance, mass of the working substance, that is m is equal to 1, we know that the total energy entering the control volume per kg of the working substance is given as E1 equal to internal energy plus displacement work plus kinetic energy plus of potential energy plus of heat supplied, and that can be given as E1 equal to U1 internal energy, displacement work P1 V1, kinetic energy V1 square by 2, potential energy GZ1 plus of heat supplied Q1 to 2, that is in kilojoule per kg we have to take. Similarly, the total energy leaving the control volume per kg of the working substance is U2 E2 is equal to U2 internal energy plus displacement work, kinetic energy and plus potential energy, work output. That is in kilojoule per kg we are going to take. Here, assuming no loss of energy during the flow, that means it is a steady flow energy condition. Steady flow condition, we are going to take the steady flow energy, and that's why it is a steady flow conditions. For that, there is no loss of energy. So whatever the energy at the inlet is there, that is equal to the energy at the outlet. Then, according to the first law of thermodynamics, we can write E1 equal to E2. Then that can be written as U1 plus P1 V1 plus V1 square by 2 plus GZ1 plus Q1 to 2 is equal to U2 plus P2 V2 plus of V2 square by 2 plus GZ2 plus of W1 to 2. We know that U1 plus P1 V1 equal to H1, that is the enthalpy of the working substance entering the control volume in kilojoule per kg, and U2 plus of P2 V2 equal to H2, that is the enthalpy of the working substance leaving the control volume in kilojoule per kg. Now, therefore, we can write, substituting H1 and H2, we can write the equations. Those are H1 plus of V1 square by 2 plus of GZ2 plus of Q1 to 2 is equal to H2 plus V2 square by 2 plus of GZ2 plus of W1 to 2. This is the steady flow energy equation for unit mass of the working substance. When this equation is multiplied by the mass m, then we get the total energy input and total energy output. Here we will take that is m1 h1 plus of v1 square by 2 plus of gz1. This term only we are multiplying the m1 because the heat energy we are going to take, that is the total amount of heat supplied, not per kg of the working substance heat supplied what is there. If you take the per kg of the working substance the heat flow, then also we have to multiply this mass. Okay, that consideration we need to take, whether we are taking this heat flow for per kg of the working substance or total heat supply. We need to take the total heat supply. If you take that one, then we should not multiply this m1 to this. Then m2 plus multiplication of the h2 plus of v2 square by 2 plus gz2 plus of w. The work done is also not taken for the per kg of the working substance. It is the total work output we are going to take. Then, but in a steady flow process, m1 equal to m2. Therefore, we can write m h1 plus v1 square by 2 plus of gz1 plus of q is equal to m h2 plus of v2 square by 2 plus of gz2. And these h1 and h2 what are there? This can be taken as the u1 plus p1 v1. Okay. In that terms also we can take, and this h2 is equal to u2 plus p2 v2. u2 plus p2 v2, we can substitute these values. Okay, these values what are there? If you take that one, in that terms also we can write the h1 and h2, the steady flow energy equations. Okay, in these two terms we can take. This is the final steady flow energy equation, okay, which we got for the particular flow system, and this equation can be applied any flow system, and there the energy availability will be different, and those energy availability if you substitute, then we are going to get the steady flow energy equation applicable for the particular that system. Thanks for watching. If you like, share, subscribe and comment.